through the use of contrived reverse engineering mathematics, if you reverse the order of integration, it turns into something that's entirely feasible. So you're prompted here to integrate y first. What's the problem with trying to integrate x squared sine of y cubed, x cubed sine of y cubed with respect to y to begin with? What is your potential integration snag there? Here's the hint, you can integrate it. Why? Be really, really nice if something else was in there. What would work well with integrating sine of y cubed?
Y squared.
Yeah, if you had at least a free-floating factor of y squared kind of wedged in there, the sweet spot would have a 3y squared. Because you choose u to equal y cubed, du would be 3y squared dy, and then you could integrate that sine of y cubed with the u substitution, reversing the chain rule, okay? But I don't have that in there. I can't just arbitrarily fudge with variables because that's like, you know, calculus faux pas from really bad. Don't do that. You only fudge with constants. Even fudging with a variable that's a constant, don't do that either. That's kind of dangerous as well. So you can't integrate this with respect to y in its original form. So in this problem, what you want to do is go ahead and take the limits on your integral and graph the region that you're going over so that you can change the limits, and then hopefully it works out the other order to where, because integrating x cubed first is much easier. Integrating x cubed treats that sine of y cubed a constant, so you do power rule and maybe something magic happens if you switch the order of integration. Let's check it out and see. The original order, dy, bless you, dy first, then dx. Y enters whatever this region looks like. Y enters at the boundary y equals x squared, and y exits at the boundary y equals 1. So go, you know, one variable pair at a time. Just go ahead and graph what this region looks like before you even look at your x limits, okay? If I graph this completely, the bottom boundary is the parabola y equals x squared, which is apparently very popular with double integrals. This has popped up in several problems tonight. The top boundary is y equals 1, horizontal line that would kind of cap off the parabola like this. Okay, but then you have to cross-reference it with your x limits of integration. Are we going to need that entire space? No, the x limits begin at 0 and they leave at 1. So when this region is flattened to the x-axis interval that you should see begins at 0 right here and stops at that point where x equals 1. Now, very important question. Let me shift this down so I can zoom in on it a little bit. Is there anyone, and it's perfectly okay to say yes to this question, is there anyone who was tempted to use this as your region of integration? Okay, that happens a few times along the way. I want to kind of address potential mistakes I've seen students make in the past. So is everybody clear on why that is not the region of integration here? It's all dictated by those y limits. The first thing and the only first thing y hits is the parabola. So the first thing y should hit as you enter this is that parabola, and that's consistent here. The last thing y should hit is y equals 1. So that much, the full parabola and the horizontal line guarantee those y limits being satisfied. But then cross-referencing with this, you don't want negative 1 to 1 for x, you want 0 to 1 for x. So that's why it's just the right half of that parabola, or that two-dimensional parabola space. Okay. So those are the original limits. But limits there are actually worthless in terms of the original order of integration. So we want to switch it to doing dy, dx, then dy. Okay, so now starting with this as our space that we're integrating with. If I go in the x direction first thing you hit is the y-axis. So x equals 0 is your entrance boundary, loving a lower limit of 0. Your exit boundary for x is going to be, the positive square root of y. So if you don't mind, I'm going to write that as y to the half, because that's the way I'll enter it when I do my integration. Okay. And then when this is flattened to the y-axis, what are your remaining y limits?
0 and 1.
Yeah, because that corner point right there is at the point 1, 1. So it also turns out to be 0 to 1 for your y limits of integration as well.
Won't your bottom one always be the same?
You mean this and this?
Yeah.
Not necessarily so. Because, yeah, what if we stopped at y equals 2 instead of y, or y equals 4 instead of y equals 1? If we went all the way up to y equals 4, the original x limits would be from 0 to 2. But then the corresponding y limits have to be from 0 to 4.
Okay.
So it only works in a handful of cases of things that intersect at that convenient 1, 1 point.
Okay.
Just unique to this problem. So, yeah, this generalization is this and this aren't always the same. They happen to be the same in this one, so just be careful about making that gospel truth. So, now committing to a new order of integration, this becomes the integral 0 to 1 my outer limits, 0 to square root of y my inner limits, x cubed sine of y cubed, and we're doing dx dy order now. So that way, when I integrate this with respect to x, first, that sine of y cubed is just a constant. I don't have to face, the integration kidney stone that it apparently is. So x to the third becomes 1/4 x to the fourth sine of y cubed, and some of you are probably already seeing how these are kind of reverse engineered and contrived. When you plug those limits in for y, your square root of y gets fourth powered there, turning it into y squared. Works really well with that use. So yeah, in just reversing the order of integration, it works out pretty well. Y to the half to the fourth is going to give you a y squared. Sine of y cubed is your constant. 0 plugged in for your x, wipes everything out. And so that's what you end up having to integrate with respect to y. So, we do a little goofy character turn thing here. And actually, in this case, I'm going to pull my quarter to the front because I'm anticipating the need for a u sub here. So does everybody see what I've done? I'm just integrating y now. Brought my quarter out. I've got y squared paired there with dy. I've got my sine of y cubed right here because this is lending itself to this u substitution. Oh no! Hang on. Last example, so I'll finish it pretty quick. I want to let u equal y to the third, and that means du replaces 3y squared dy. And again, this depends on your calculus 2 u substitution experience. The way I teach it is I tell my students to, if you have any constants that you need to kind of multiply in there, counteract them with the reciprocal in the front. Like I want a 3 there with my y squared so that becomes my du. So the way I teach it in Calc 2 is I tell them, put the 3 there when you need it, cancel it out in the front so everything's still balanced, and that technically becomes a coefficient of 1/12. True. So that way that becomes sine of u, 3y squared dy properly becomes du. And there's one big important thing I've forgotten. This is a definite interval. You had limits of 0 to 1 for y. What would those correspond to the u limits here? Yeah, a 0 limit there for y. Use your u substitution to change the limit. Have you done that?
Right, yeah.
So at y equals 0, u would equal 0. And conveniently enough, at y equals 1, u would equal 1 cubed. So you actually end up with the same limits on the u interval that you had on the y. That way you don't have to undo your u sub when you're done. So you integrate your 1/12 sine. Oops, I almost screwed up. Negative 1/12 cosine u. Okay, you get a funky answer. You end up taking the cosine of 1, meaning the cosine of 1 radian. And then minus negative 1/12 cosine of 0. Cosine of 0 is 1, so you end up with that as your answer. it's kind of funky to see, you know, a rational number plugged into a trig function, but that's what that means. That's just cosine of 1 radian, whatever that number is. That's not one of those special angles I knew from the unit circle, so I'm just going to leave it as the value cosine of 1. And then cosine of 0, remember that becomes a 1. Cosine and e, watch out for plugging 0 into them, they don't wipe out. So that is the correct value of this integral that previously could not be evaluated. So approach the double integral supplemental problems with well, studious reference abandon, and get as many of those done between now and Thursday as you can. So what I'm going to need to do, in case you missed the announcement, I'm going to need to wedge the topic of polar coordinates and double integrals between this and triple integrals. Because, well, it's really that way in the textbook. It was that way on my original outline. I thought I could interchange them. Can't do that. So I'm going to have to do double integrals and polar beginning class on Thursday. And that's most likely going to be on test 3. So I'm thinking of maybe moving triple integrals to the first topic of test 4. And just switching the position of those two.
Test 3 on this Thursday?
No, test 3 will end this Thursday. Whatever I finish this Thursday night ends test 3's material. I'll begin it being available in the testing center on Saturday through Monday, Tuesday, and Wednesday of next week. Okay. Y'all take care. Have a wonderful evening. And email me if you have questions, and I'll see you Thursday.